Hello, my name is Goel. I'm a postdoctoral researcher at the University of Oxford. In this video, I will present a brief overview of our paper Data-Centric Factors in Algorithmic Fairness, which is a joint work with Nianyun Lee and Elliott from ETH Zurich. For most of the computer science researchers working in the field of AI/ML fairness, these words like adult, compass, German credit would perhaps sound very familiar. These are so-called benchmark datasets very commonly used in all AI/ML fairness papers. Most of these papers follow what may be called an algorithmic centered approach to AI, where the data remains the same and we play with different algorithms to see which one works best. A complementary approach that is emerging in AI/ML research is the data-centric approach. Here, the focus is also on various data-related factors that influence models' performance. It is a commonly held view that data generation and curation processes are among prominent sources of bias in algorithms. We thought it might be useful to empirically understand and document the extent to which various data-centric factors have an effect on the fairness and accuracy of different machine learning algorithms, and how these data-centric factors interact with fairness interventions and other algorithmic design choices. Another important contribution in this paper is a new, much bigger and diverse dataset for fairness research. I will focus mostly on the first point in this short presentation. The dataset used in this paper has been obtained through the Wisconsin Circuit Courts Access API. It indexes public case records and docket information from 72 county courts in the US state of Wisconsin. We collected records of cases filed from January 1st, 1970 through December 31st, 2020. There are 11 million records, 2.5 million of those are criminal. We have defendant's name, date of birth, gender, race, and address. We also have charges in current offense, decisions, and sentences, etc. There are several other details in case records, like the name of the judge, attorney, prosecutor, information about bail hearings, amounts, sentencing and probation, records about incarceration and parole, and many other events. Not all the information is used for the analysis presented today. We process these raw case records that you can access through the API to prepare a machine learning dataset. Some of the features were directly available, other features we had to build. The entire processing is described in detail in the paper. After the processing, for each row in the dataset, we have the current offense, the prior criminal history, gender, race, and age. We also added additional local demographic attributes from census data. These attributes include population density, proportion who attended college, proportion eligible for food stamp, African American population share, Hispanic population share, proportion of male, proportion who live in rural and urban areas, and median household income. In addition to the features, we have a target variable that we want to predict. In this case, a typical task is to predict recidivism. Now, this variable is not directly available in the dataset, and we had to make a lot of choices there while defining the variable. Again, details are in the paper and I encourage you to read that too. Those are important details which I am not covering due to short nature of the presentation. Let me give a quick summary of the dataset that we prepared. The dataset has 1.5 million rows. It consists of 5 racial groups. The Caucasian group with 65% share, the African American group with 22.5% share, and other groups that include Hispanic, American Indian or Alaskan Native, and Asian or Pacific Islander. Recidivism rate, as observed in the dataset, is the highest among the Native Americans, followed by the African Americans. The male population is significantly higher than female. Most of the population is below 60 years of age, and below 30 years is generally the majority. There are three case types in the data: felony, misdemeanor, and criminal traffic. Share of misdemeanor cases is higher overall and for most racial groups as well. We used two kinds of classifiers in our experiments: the logistic regression and the XGBoost classifier. For measuring performance, we used accuracy and AUC metrics. For fairness, we used false positive rate difference, false negative rate difference, positive rate difference, and bias amplification. The details about implementations of the classifiers as well as about the performance and fairness matrix are in the paper. So what we did first was to just see if we train a machine learning model on this dataset, how does that perform? Let me hide the lower part of the table, which contains results for the logistic regression classifier, and just focus on the upper part of the table, which has results for the XGBoost classifier. I'll read out some of the parts of the table. We observe that the Native American is the most disadvantaged group in the sense that it has the highest false positive rate and positive rate, and the lowest false negative rate. The largest false positive rate difference is around 13%. The largest false negative rate difference is around 18%, and the largest positive rate difference is around 20%, all between the Native American group and the Hispanic group with XGBoost classifier. Hispanic and Caucasian groups receive the most favorable decisions in both models, followed by Asian and African American groups. The overall accuracy of the XGBoost and the logistic regression classifiers is not very different, but the false negative rate, false positive rate differences between the groups is higher for the XGBoost classifier. In the rest of the paper and the presentation, we focus mostly on the Caucasian and African American groups, mostly because these are the two biggest groups in the dataset. I will not cover all the results that we have in the paper. I will just show three results in the next 3 slides. The first result that I am showing here is about the role of group proportions and base rate differences across groups in the training data and in the test data. In our experiments, we do not assume that train and test datasets come from the same distribution. For the experiments, we simulated different data settings using sampling methods, such as if group sizes are equal or unequal but in the different direction, if base rates are equal or if base rate difference increases even further, if the outcomes are balanced, that is, the group sizes are equal as well as the base rates are also equal. In all the cases, the first thing we can observe is that the overall AUC is much or less unaffected, whereas the fairness matrix, like the false positive rate difference, false negative rate difference, and the positive rate difference, change quite a bit. We also observe that some fairness matrix, for example positive rate difference, as expected, is more sensitive to the distribution shift problem. The second factor that we are looking at is the temporal dimension of the dataset. Instead of just training and testing over all the years of data, what we did was that we trained on a 2 years window and tested on next 2 years after a 2-year gap. And we moved this window over the entire period during which the dataset was collected. Here also we can see how much fairness metrics change over time, from almost 8% difference in the early years to 1 or 2% difference in recent years. We discuss this more in the paper, how that may be related to change in feature distribution or the way that this data is curated or collected over time. The third result that I am showing here is the role of including additional attributes in the model. The additional attributes are the race variable and the local demographic variables that I mentioned earlier, like population density, proportion who attended college, proportion eligible for food stamp, African American population share, Hispanic population share, proportion of male, proportion who live in rural and urban area, and median household income. What we are observing here is that including race makes the model a little bit more accurate, but a lot more unfair. On the other hand, Including other variables actually makes things a bit more fair. It probably hints that the model may be correcting for the confounders using these additional variables. Overall, this shows the role of feature selection and feature curation in the dataset. We have several other observations in the paper, for example, about the role of sample size, the role of type of offense, and whether there are separate classifiers for different groups or not, and so on. I encourage you to read the full paper available at my website for more results, related work, and other details. To conclude, we presented a simulation-based study of data-centric factors in AI ML fairness on a big new dataset. The main conclusion is that data-centric factors in the context of fairness deserve independent attention in research and in practice. Many times when we saw no effect on overall accuracy, there still was significant variation in fairness measures with different data-centric factors. We think further research in this direction can help us in understanding the meaning of good data quality in the context of AI ML fairness. Perhaps not in the sense of guaranteeing fairness of algorithms trained on this data, but quality data as a minimum requirement to do reliable and comprehensive empirical research on algorithms. This leads to the second question: what are the appropriate evaluation and benchmarking methods for fairness algorithms? And finally, the complementary theoretical analysis of these data-centric factors. We hope that this further research will help in the development of robust, fair algorithms. Thank you.